Assalamualaikum warahmatullahi wabarakatuh, and good morning to all my students. Today's lecture we're going to cover chapter 2, which is Introduction to Chain Growth Polymerization. Now we look at the lesson outcomes. At the end of the subchapter, students should be able to briefly explain the effect of substituent groups towards choice of initiator in polymerization. List and explain the characteristic of chain growth polymerization. Write the polymer repeating unit for chain growth polymer. Briefly explain the mechanism in chain growth polymerization and also distinguish between step growth and the chain growth polymerization. So we have covered about step growth polymerization. Now let's look at the introduction to chain growth polymerization. Okay, the mechanism of the chain growth or the principle of the chain growth is it is the addition of the monomer to a growing chain, and the polymerization can ensure by an addition to a polymerizable group, especially an olefin double bond, or by the opening of a ring. So the requirement for the chain growth polymerization, the monomer you use must contain double bond, or else you want to opening a ring of certain compound, for example this epoxide ring. So we can use the chain growth polymerization method. The double bond of olefin is converted into two single bonds because in the case of carbon, two single bonds have less enthalpy than one double bond, and the reaction is very exothermic reaction, which is required high temperature and easily increase temperature. In converting the double bond of monomer into single bond, it needs initiator to break the double bond to produce polymer rapidly, as compared to step growth polymerization. Growth does not require any initiator to polymerize the monomer or to polymerize the polymer. In chain growth polymerization, break a carbon double bond of monomer to make a polymer can be by homolytic or heterolytic fission. The heterolytic fission, also known as the heterolysis, it is a type of bond fission in which a covalent bond between two chemical species is broken in an unequal manner. It will resulting in the bond pair of electron being retained by one of the chemical species. So actually the hetero word it from the Greek word means that different, and it is the process of cleaving a covalent bond where one previously bonded species take both original bonding electron from the other species. So in heterolytic fission, ions are formed. As we can see, the ion here are formed, and one atom takes away the electron pairs. As compared to the homolytic fission, we can see that the carbon with the ion, not ion, it is carbon with the free radical. Okay, free radical are formed, and it is initiated by heat, light, or initiators like peroxide and so on. And homolytic fission is faster compared to the heterolytic. For the definition, homolysis or homolytic fission is the chemical bond dissociation of a molecule by a process where each of the fragments retains one of the originally bonded electron. So as we can see, this double bond, when it is break or the bond breaking, the double bond is break. So each electron or each free radical will go into each carbon bond. Okay. Call it as the unpaired electron denoted by this dot here. And the carbon double bond of the monomer that break by homolytic fission may ensure the free radical polymerization. Radical polymerization, if you notice that this arrow is half arrow, means that it is the movement of the radical or one electron into the other. Initiator together with the radical will attack the double bond of the monomer, and we produce polymer with the initiator together with the unpaired electron. This is for homolytic fissions. Now we look at heterolytic fission. The carbon double bond of monomer that break by heterolytic fission may ensure the ionic polymerization. So compared to the homolytic fission, the heterolytic fission is shown in the full arrow nominated by the two electron. And it is depend on the electronegativity of that ion. So heterolytic fission is in the ionic polymerization, which is one of the chain growth polymerization method. The monomer that has been attacked by the initiator called as active center or active site. The active center usually have high energy and unstable, which is able to add to a monomer unit and thereby transfer its active character to the newly incorporated repeating unit. So the active center will add to the monomer and it will propagate and then it will produce another polymer. It also must stable, which is have long shelf life to persist through multiple monomer additions. This leads to a chain reaction in which the growing chain continuously add additional monomer units until no more monomer is available or side reaction occur. So the principle of the chain growth is the addition of the monomer together with the active center to attack another monomer to produce a growing chain and finally to produce a polymer at the end of the termination process. Now we look at the choice of the initiators for chain growth polymerization. It required an initiator to begin the reaction. For example, we have peroxide here. The choice of initiators fall into three general categories, which are free radical, cationic, and anionic. The choice of the most appropriate one depends largely on the substituent group, the monomer, and their effect on the double bond. First, we have electron withdrawing group, and the second one is the electron donating group. Electron withdrawing group reduce the electron density at the double bond by withdrawing the electron. And electron donating group increase the double bond nucleophilicity by donating the electron. So both groups alter the negativity of the pi bond electron cloud and thereby determine a radical and an ion or cation will be stabilized. In general, an ionic initiator encouraged to attack electron withdrawing group, while cationic initiator encouraged to attack electron donating group. The free radical initiator is generally useful initiator because most substituent can provide some resonance stabilization. This one is the characteristic of chain growth polymerization. One molecule species in the mixture can react with presence of initiator or also known as a catalyst. The growth occurs by random addition of monomer units to very small number of growing chain. The activation energy of rate for chain initiation is much greater than the propagation. The average molecular weight increases rapidly with reaction time, exception for leaving polymerization, and the monomer consumed relatively slow, decrease with reaction time. And last one, polymerization rate increase initially as initiator units generated remains relatively constant until monomer is depleted. This is the commercially important polymers prepared by chain growth polymerization. We have ethylene, propylene, isobutylene, styrene, vinyl acetate, acrylonitrile, vinyl alcohol, vinyl chloride. So you need to know or familiarize with the structure of the monomer, okay, to become this polymer. You need to familiarize with the monomer structure. Now we look at the mechanism of chain growth polymerization. We will cover free radical, cationic, anionic, and also the coordination. Some monomer will not polymerize by more than one mechanism. So there might be, for example, polystyrene. It can be polymerized by free radical or cationic. So either three or two of the types of polymerization. Structure of the monomer and its electronic and steric situation affect the thermodynamic and kinetic of the polymerization. All reactions except for leaving polymerization in chain growth will be react by the following mechanism. We have initiation, propagation, termination, and by chain transfer. Of course, during the initiation, it is a step where the generation of the active initiator. So during the initiation process, the initiator is activated first to be reacted with the monomer to form a growing chain. And then this growing chain will produce the propagation step in which the growing chain will interact or react with the monomer itself, and it will produce the monomer with a growing chain. And it will propagate to produce a polymer, and then we terminate in the termination process, which is the conversion of active growing chains to inert polymer. And when the termination process is complete, the polymerization cannot proceed further. For chain transfer, it is the transfer of active growing site by terminating one chain and reinitiating a new chain. So termination, we have a termination by chain transfer. It is the one types of termination which is by chain transfer. This one is the illustration to show the comparison between step growth and chain growth polymerization. As we can see in the first figure, here is the reaction of the monomer for step growth. It did not require or initiator. For chain growth, it required initiator to be reacted with the monomer. And we look at the second figure, second image here. As we can see that high molecular weight is obtained initially and continuously during the chain polymerization process compared to the step growth, which is the molecular weight increases with the conversion and it is slowly reacted. And we look at the third image, which is you can see that the in-chain growth polymerization reaction mixture contains only high polymer, monomer, and reactive species is actively reacted to form polymer. While here monomer concentration start to decrease rapidly, and the reaction mixture contain a range of different size species. And at the end of the reaction, the polymer will produce. At the end of the reaction in step growth polymerization and chain growth polymerization, it produce the high molecular weight polymer is produced continuously, even at the early stage of the reaction until the termination process is completed. Okay, any two molecular species in the mixture can react in the step growth polymerization, while in the chain growth, any molecular can react. It reacts with itself with the presence of the initiator. In step growth polymerization, chain growth is usually slow and polymer molecular weight rises slowly. And for the chain growth, it is usually very rapid. Polymer molecular weight begins to form immediately the reaction begins. In step growth, no initiator needed. In chain growth, initiator needed to make active center can react with monomer and add units onto the chain one after the other and different mechanism throughout. Okay, I think that's all for the introduction. We will proceed with the free radical polymerization.